Welcome back to the channel. Today, we're going to take a look at an alternative solution to keep the little battery charged on the gasoline electric golf cart. Now, if you're new to the channel, well, here's a quick backstory on this one-of-a-kind electric golf cart. So we completely removed the heavy and expensive lead-acid batteries and replaced them with a 212cc Predator engine and a modified 140-amp alternator from a Jeep Liberty. Now, the engine and the alternator combination provide us with all the electricity that we need to get this golf cart back on the road, and best of all, we'll never need to buy batteries again. Well, the truth is, we do have a small battery on board to power the electric starter and to power the simple electronics that we're using. Now, to make this golf cart usable for daily driving, we're going to need a way to keep the little battery charged. Today, we're going to play around with an alternative method to charge the battery. I think this alternative method may be more in line with simplicity because it's a nuts and bolts solution. So this video primarily deals with what's involved in building a gasoline electric golf cart. However, there may be some folks tuning in just to see the high-powered battery charging system that we're going to be installing on the 212cc Predator engine. So if you're here for the details on the charging system, jump to this part of the video and you don't have to hear me pontificate on stuff that really doesn't matter. Now, in a previous video, we came up with a low-cost solution to keep the battery charged, and the concept was to skim some of the power from the modified alternator and feed it to a buck power supply. Now, since the voltage that was coming out of the modified alternator was noisy, and we had a massive amount of ripple, well, we ended up filtering the voltage with a diode and a capacitor. Then we pumped that voltage into the power supply. We also had to use a relay to disconnect the power supply when the golf cart was parked. So to me, this makes a lot of sense, and that's because I have a background in electronics. I really tried to make the system as simple as possible, and I used all off-the-shelf parts. However, there's a lot of wiring involved, and the power supply needed to be programmed via these buttons. Perhaps this ain't the greatest solution, because even though it's simple for me, well, it may not be simple for folks without an electrical background. So today we're going to look at a nuts and bolts plug-and-play solution, and to be honest, I like this solution much better, but it's not low cost. Anyway, after I got done building the low-cost onboard charging system, I spotted this alternative solution and I had to give it a try. Now, this channel has a decent sized audience, and I could have used my YouTube credentials to get VIP service, but that's not how I roll. I wanted to have the same experience the audience has, so I ordered this stuff incognito. In other words, the vendor had no idea these parts were going to appear on a YouTube video, and that's perfect because I wanted to share my honest opinion with you folks. Now, this box full of goodies was shipped out of Hong Kong the day I ordered the parts, and it arrived at my doorstep a week later. So shipping was extremely fast considering the distance from Hong Kong to Wichita, Kansas. Now, this little box was expensive to ship, and shipping was $64, but I think it was well worth it. Okay, so here's the Flywheel. Now, this Flywheel is made for a non-Hemi engine and it has a ring gear for an electric starter. What makes this Flywheel special is it has 6 magnets instead of the normal 2 that are found on most 212cc Predators with an electric start kit. The vendor also sells Hemi flywheels and flywheels without ring gears if the electric start is not your thing. Now, this thingy is an 8-pole stator, and if it's used with the special Flywheel, well, the vendor is claiming you can get 10 amps out of the system. We'll find out if that's true or not later in the video when we test the system. So it uses two 30mm M6 fasteners to mount it to the engine, and unfortunately the fasteners are not included, but it does have a very nice connector that plugs directly into the rectifier. So as I mentioned earlier, this rectifier is made for a more powerful 25 amp system, but it should be fine on a 10 amp system. This green wire connects to the negative terminal on the battery, and this red wire with the fuse connects to the positive terminal on the battery. And finally, this connector plugs directly into the stator. Now, there are no instructions included with this pile of parts, and it's assumed you have knowledge of how to install all this stuff. And there you go, a bolt-on plug-and-play system for the 212cc Predator that will generate up to 10 amps. Now, the rectifier costs $31.99, which seems like a great price. The stator costed $35.99, which is also a great price, and the special 6-magnet flywheel with a ring gear costed $39.99. All in all, it was $107 for the parts plus shipping. Now I'm going to leave a link for the parts that I used in the video description. Keep in mind, the parts I'm using are for a non-Hemi engine and I chose a flywheel with a ring gear. If you have a Hemi engine, well, you're going to need to get a flywheel that's made for the Hemi. And if you don't need a flywheel with a ring gear, well, they sell those as well. Let's see if these parts will fit the Predator engine and if we can generate the claimed 10 amps. So off camera, I took the plastic body off the golf cart. Now, the 212cc Predator engine that we're using has already been fitted with a low-cost electric starter kit, so we didn't need to purchase a starter. All we really have to do is pull off the old flywheel and install the new stator and the new flywheel. And it looks like it's going to be difficult to pull a flywheel with the engine in place. I reckon it could be done, but it's going to be hard to video all the details. So let me pull the engine out and we can fiddle with it on the bench. Fast forward a few minutes and the engine's out of the golf cart. Now, pulling the engine was a lot easier than I thought it would be, and that was nice. Let's zip the cover off so we can get to the flywheel. Now, to pull the flywheel, I'm going to use the hammer and screwdriver method. Notice that I'm using a soft-faced brass hammer. So with a few hard swings on the crankshaft with the hammer and some pressure being applied to the flywheel with the screwdriver, we're able to get the flywheel to pop off the crankshaft. You do this enough times, it's actually easy, but keep in mind, never hit the flywheel with the hammer. Whoops, looks like the magneto's in the way. Now on an engine with an electric starter flywheel, the magneto needs to be removed in order to provide clearance for the ring gear. There we go, the magneto's removed and now we can remove the flywheel. So this engine was already equipped with 2 standard charging coils. These coils can provide a maximum of 2 amps, which isn't enough for our application. We need about 4 times that amount of power in order to keep the battery charged when the golf cart is moving. So I'm going to pull these out and put them in my part stash. Perhaps they'll come in handy for another project. Now right here is a little aluminum wire shield and we're going to need that later. So here's the flywheel we just removed from the engine, and as you can see it only has 2 magnets. And this is the new flywheel with 6 magnets. So when the flywheel rotates, the magnets will move past the coils on the stator, and this is basically how electricity is produced. Now having a lot of magnets and a lot of coils means we're able to produce a lot more electricity, and that's exactly what we want. Now it looks like the ring gears are the same size, which is more good news. Alright, let's make sure that the plastic cooling fan fits the new flywheel. So it fits the old flywheel like this. Let's see how it fits the new flywheel. And it fits fine, so the plastic cooling fan will work on this new flywheel. Let's see if the flywheel will fit the crankshaft on the Predator engine. And it sure does. There is a little bit of a wiggle, but that's also present with the other flywheel, so I'm calling that okay. Now, some people use valve lapping compound to get a perfect fit, but I'm not doing that today. This is fine. Now let's see if the stator fits. So the bolt holes line up, and that's good. I was actually worried about that. Alright, let me fast forward through this part while I figure out how the stator is supposed to fit. I'll show a close-up of what I came up with in a moment. So like I mentioned earlier, it's going to take 2 M6 by 30mm bolts to secure the stator to the engine. Now fortunately, I was able to find these bolts in my stash of metric nuts and bolts. Alright, I worked out all the details, and for the best fit, the yellow wires need to be pointing down like shown. The stator will fit many different ways, but this appears to be the best way as far as routing the wires go. Now, if by some miracle you actually have the aluminum wire shield, it fits like this. The harness passes through this shield through a hole that's hidden by the wire shield. Now, all of these shields came with the original electric starter kit and were not included with the stuff I just installed. Anyway, the stator fits the engine perfectly, which is quite a relief. Now, since I have the flywheel off, perhaps now is a good time to install an offset crankshaft key. Now, this key has nothing to do with the stator we just installed. It's a performance modification. You see, the offset crank key provides a way to advance the ignition timing, and there are many different offsets available. However, this engine is completely stock, and we don't intend to run it past its 3600 RPM limit, so we're going to use a 2-degree offset. And this will advance the ignition timing by 2 degrees. In this case, a little bit may be okay, but a lot of advance would likely cause problems on an unmodified engine. So the crank key fits the crankshaft like this. If you put it in backwards, well, you would be retarding the ignition timing by 2 degrees, and that's not good. And when I zoom the camera out, you can see that the arrow is pointing towards the front of the engine. Got it? Good. Let's continue. So you gotta be careful when installing the flywheel. Sometimes the flywheel can push the crank key out of its groove, and at that point you have nothing to keep the flywheel timed with the crankshaft, and the engine probably won't even run. Now I'm gonna zip the crank nut on in order to seat the flywheel. And now the flywheel is swedged onto the crankshaft, and all is good. Let's put the engine back together. So the magneto needs to be properly spaced a certain distance from the flywheel. You can use a credit card or a business card to set the spacing. I'm using poster cardboard because I got plenty of it and it was handy. And just to make sure nothing hits, we'll run the ignition magnets past the magneto, and sure enough, we have ample clearance. So I think we're done with the hard stuff, and now all we have to do is install the cover and we can test the engine and the new charging system. Okay, let's do one last quality control check, and I'll pull on the starter rope. And there's no noise of part scraping, and obviously that's good. So it looks like we were able to put this engine back together without any issues. Now let's see if it'll run. Fast forward a few minutes and I have the engine mounted to a bench and it's ready to run. Since there's no fuel tank, well, we're feeding the engine gasoline from an IV. Okay, so for the first test, I want to look at the raw voltage that's coming out of the stator. Now this is completely unnecessary, but it's interesting data to have in the memory bank. So we need to set the meter to AC volts right now. And at idle, it looks like we're getting 15 volts AC, which is good, very good. Let's see what we get when the engine's at full throttle. And it looks like we're getting about 25 volts AC. Now once this AC voltage passes through the rectifier and the regulator, it should be converted to a normal DC voltage that's okay to feed to the battery. Alright, let's connect the rectifier to the engine and the battery and see if we can get 10 amps out of the system. So for this test, we have the yellow wires from the rectifier plugged into the stator on the engine. And we have the red wire from the rectifier connected to the positive terminal on the battery. Next, we have the green wire on the rectifier connected to the negative terminal on the battery. And this is how the rectifier should be wired so it works properly. Now we also have a multimeter connected to measure the voltage between the rectifier and the battery. Now this meter actually talks and it's going to be annoying. So if you hear a robot voice in the background, well, it's the meter talking to nobody. It's just going blah 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 blah. It just talks. Now this red wire, well, we're going to pass this one through the fluke meter, and that's so we can measure the amps that the rectifier is sending to the battery. Now, unfortunately, this fluke meter can only measure a maximum of 10 amps, which in our case is perfect, and I'm going to try to get this as close to 10 amps as I can. Now, I really don't have a good way to put a perfect 10 amp load on the system, so I'm going to have to improvise and discharge the battery a little bit so the rectifier will have some work to do to get the battery back to normal voltage. Now, I'm also going to put a resistor load across the battery to make up for the difference, and together we should have something that's close to a 10 amp load. Meh, if you had no idea what I just said, well, that's okay. The bottom line is, we're going to measure the output of the charging system and see if it provides the claimed 10 amps, and this experiment will provide us with that information. Okay, fast forward a few minutes and I have the system connected exactly like I showed in the diagram. And over here we have the load resistors cooking away and draining the battery. Now, if you look closely, one of the resistors is actually smoking, which is probably not good for the resistor. And over on the voltmeter, we're showing that the battery's down to 11.82 volts. Nice. So what that means is we're going to be starting this experiment with a partially dead battery, and that's exactly what I want. Let's go ahead and start the engine and see what happens. Okay, so at low idle, we're showing about 2 amps on the fluke. This is normal for the charging system at idle. Alright, let's get the engine up to speed and see what we get. Wow, almost 10 amps. Not too shabby. Now the voltage actually looks okay, all things considered. So far, so good. Let me disconnect the resistor load, and at this point the system will be just charging the battery. And as you can see, the current's going down, which is to be expected because the battery is successfully being charged. Now, the more the battery gets charged, the less current we'll see on the meter. And the voltage looks great. Very nice. Let's let the engine idle and see what we get. Nice, very nice. And the rectifier is only slightly warm. So it looks like we have excellent voltage regulation and the system is working normally. So with my hodgepodge setup, we were able to see the charging system indeed provided as close to 10 amps as I could get it. Of course, that was with the engine running at full speed. Now, when we let the engine idle, we saw the current drop to around 3 amps. This is completely normal and I'm very satisfied with that. So the maximum amount of current that the system can produce is dependent on the speed of the engine. And for such a small system, well, this is exactly what I expected. I'm going to say this passes the robot Cantina bench test and we're good to install this system on the golf cart. Now, I have absolutely no affiliation with the seller, and I'm providing the links to the parts I used as a courtesy to the viewers. Now, if I didn't provide the links, well, I would get a bunch of requests for them. So the links are in the description and have at it. As far as I'm concerned, this stuff works exactly as I expected it to. Now, I think I like this system a lot better than the power skimming method that we were using. So I'm going to remove this stuff and possibly use it on the diesel-electric Cushman Desperado. Oh, and we do have an update on the Desperado, and I'll talk about that in a few moments. Now, before I put the petroleum battery back in the golf cart, well, I figured I'd show you the size difference between the small block 212cc engine that we're using and the 420cc big block. So yeah, the 420cc engine is huge, and it would take a lot of effort to get this thing to fit in the same space as the 212cc engine. The real question is, how much better would the golf cart perform with the 420cc engine? Well, I hear you, big dog, and we're going to test the 420cc engine on the Cushman Desperado. Now, the 420 is not going to fit in the Cushman in a nice way, but that's okay. You see, we're going to mount the big block on the back deck of the Desperado. Now, it's not going to be pretty, but the Desperado is not a pretty golf cart. And best of all, we can leave the diesel-electric petroleum battery in place so we can continue developing the diesel version of this insane contraption. So look forward to the 420 experiments coming up soon. Alright, back to the task at hand. So off camera, I went ahead and installed the petroleum battery in the nicer golf cart. I ended up mounting the rectifier to one of the seat supports. Now this ended up being the perfect place for this thingy. If you noticed, I also took the recoil starter off the engine. Now, since we have an electric start, we really don't need the pull starter. But the main reason for this modification was to get the engine to run a little bit cooler. In the past, well, we've done experiments and there's a big temperature difference with the recoil removed. So right now we really don't have any issues with overheating, but next week it's going to get close to 80 degrees Fahrenheit and we want to take this buggy on a fuel economy and durability test out in the hinterlands of Kansas. And just to be safe, we're going to have the engine run a little bit cooler. Alright, right now the battery's at 12.5 volts. Let's see if the new charging system works. Oh, there we go. Let's rev the engine for a moment. Yep, it works. And best of all, well, this system will charge the battery when the engine's at idle, which is something the previous system couldn't do. But that really wasn't an issue, because at idle, the control system for the petroleum battery doesn't put a load on the electrical system. Now, what's nice about this new system is we probably have enough spare power to run the headlights and the taillights and not have to worry about draining the battery. So we're going to have to give that a try for sure. Now, I was about to put this thing all back together, and then I noticed this wet spot under the engine, and unfortunately it would appear the carburetor's leaking gasoline, and I'm gonna have to sort that out before I put the plastic body back on this thing. That sucks, but I can't have a fuel leak on this thing. Anyway, perhaps it's a good time to end the video. Now, I had fun today, and hopefully you did as well, and maybe even learned something. We'll see you next time. Until then.